All right, good to see you guys again. Hopefully you were able to watch the video that I posted to replace the lectures that I couldn't be here for. So I just posted one video because we're a little bit ahead of schedule, so it was okay if we missed a day. And in that video I talked about mainly, remember it was some of these training issues, and I think some of the convolutional layers stuff too. So today we're going to talk about some other networks beyond AlexNet that we learned about and kind of go through a progression of what people learned over the years and what tricks were adopted. To start out, we'll talk first about this idea of what's called transfer learning. So transfer learning is the idea that you have a pre-trained network that somebody else spent a lot of resources to train. So for example, any of these deep networks that have millions of parameters that are trained on ImageNet, which has millions of samples, this requires a lot of computing resources, not something that you or I could do on our laptops, but maybe they did this at Google or somewhere, and they published the network and the weights. So we can download those trained weights. And then what we can do is we can adapt a few layers, usually the layers at the end, to perform a new task. So let's say we download VGG and we have all the weights, but VGG was trained on 1,000 classes of ImageNet. And let's say we don't want to do that. We want to determine whether a given picture is a hot dog or not a hot dog. Let's say that that's our task, and maybe a hot dog is not in the classes of ImageNet. So what we can do is we can keep all the convolutional layers pre-trained, and we can retrain just the dense layers at the end of the network. Those are the ones that take the information output by the convolutional layers and learn how to use it for classification. So that's the idea here. We fix the early layers in the network, and we retrain the later ones, the dense ones, so that they perform well on a new task or new data. Another example is, because ImageNet, this network was trained on ImageNet, maybe we're going to give it new samples to train on that it has never seen. So that's the idea behind transfer learning. Does that idea make sense? Okay. And so, like we said, one application is we want to generate the features to use for a new learning task. And then another, maybe it's almost part of the same application, is that we only have enough data to train a few layers. We don't have ImageNet or something that size, and we don't have the computing resources. So maybe we just have a few samples of hot dogs and not hot dogs, maybe like 100, and that's maybe all we need to train our dense layer or dense layers for that new task. So there's a number of other applications of transfer learning, and if you're interested, you can click on this link here. So the nice thing about PyTorch is the torchvision.models package has many pre-trained nets that you can download, and you can play with, you can adapt some of the weights. So AlexNet we talked about. We're going to talk about all these other networks in the next few slides. And we'll also go through a demo that shows how we can download this VGG network. We can look inside it, and we can put data through it and do different things with it. Okay, so we talked about AlexNet as I think that was 2012. That was like the very first big success of a deep network in the image recognition or image classification task. So, but that was just the beginning. And so VGG was maybe the next big idea. And one of the main differences between VGG and AlexNet is VGG is using much smaller kernels. So only 3x3 kernels. Well, if you remember with AlexNet, the first layer was actually an 11 by 11 kernel. In addition, it uses more layers, 16 layers, whereas AlexNet, I can't remember exactly how it used, but it was fewer. So to understand why the smaller kernels are better, we should first think about the size of the number of coefficients and how that relates to the kernel size. So if you remember that when you have a convolutional layer, the number of coefficients in that layer equals the kernel size, let's say k times the number of input channels times the number of output channels. Okay, so you can see that this number k has a huge effect on the number of coefficients. So as you make k smaller, you go from 11 by 11 to 3 by 3, you have a lot fewer coefficients to learn. Now, the idea here is, not just to have one 3 by 3 layer, but to have several 3 by 3 layers cascaded. So, and if you think about how convolution works, if you convolve an image with a small 3 by 3, and then you convolve again with another 3 by 3 and another 3 by 3, the effective size of the convolution kernel that you're using increases, right? So because it goes like this. So if you have an image and you convolve with a kernel that is, let's say, k by k, and then you convolve with another kernel that is, we'll call it m by m, then this is the same thing as taking that image and convolving with a kernel that is of size k plus m minus 1 times k plus m minus 1. Okay, so basically, it's like the effective kernel size increases the more of these convolutions you do. Does that make sense? That's just how convolution works. When you convolve several times, it's like the width of the thing you're convolving with effectively gets bigger. So it turns out that when you have 5 convolutional layers of 3 by 3 kernels, if you apply this formula here, that's the same in terms of what they call the receptive field as one convolutional layer with an 11 by 11 kernel. Okay, so what that means is if you forget about all the activations, you remove all those nonlinear parts of your network, and you just have essentially 5 stages of 3 by 3, that's similar to one stage of 11 by 11. Okay, and so that would perform approximately the same. However, what we really have when we do this is we have nonlinear layers. After every convolution, we do things like ReLU or other nonlinear things, and as a result, when you have 5 of these nonlinear layers, they're much more powerful than one layer. 5 small kernel layers, it's much more powerful than one big kernel layer because of all the nonlinearities in between. So this is one of the things that they realized after AlexNet was designed. And this was probably the biggest idea or the main thing that you can explain the improvement in performance in going from VGG to AlexNet. It's basically deeper networks with smaller kernels. So VGG 16, so there was actually different VGGs. There's like an 11 layer, 13 layer, 16, 19 layer versions. VGG 16 achieved a top 5 error of 7.5%, whereas AlexNet got 15%. So that was a big improvement. And even today, people still use VGG, especially the convolutional layers. They use this for other tasks because the features you get out of those layers are quite good. They're quite useful. Another thing of note is that the total number of parameters did grow by a factor of 3 going from AlexNet to VGG, so that's significant. AlexNet already had a lot of coefficients. Now VGG has 3 times the number, so it's going to take longer to train and so on. This is here you can see the network. This is our color image we start with. These black layers, basically convolution and ReLU. And then you can see we decrease the image size, basically halve the image size through max pooling, go through a couple more layers, then do another max pool, go through a few more layers, another max pool, and so on, until we get something where you could say that the size of the images are very small, 7 by 7, but you have 512 channels. At that point, you go through some fully connected layers and finally 1,000-way softmax. Okay, so we'll actually take a close look at this again in a few slides. So that's VGG. Any questions on VGG? Okay. So, so from 2012 to 2014, performance got better as the networks got deeper. That's basically what we can say. But as these networks got deeper, the number of parameters was getting out of hand. We went from a 60 million in AlexNet to 180 million in VGG. And this was just too big. People said we would like to make them even deeper, but we cannot make the number of parameters bigger. We can't handle that. So basically they said we need to figure out a more efficient way of doing this. We want networks that are deep, yet with many fewer parameters, basically more efficient. And so this was accomplished with GoogleNet, also known as Inception version 1. The word Inception comes from a film around 2010 where it's kind of a meme. We need to go deeper, so that's where the name came from. But it accomplished that task with only 5 million parameters, which, as you can see, is a huge reduction from 180 million. Let's see. Okay. And also, it improved the performance of VGG by a little bit, went from 7.5 to 6.7%. Okay, so roughly equal performance, but huge reduction in terms of the number of parameters. So how did they do this? One of the main ideas were these things called inception modules. So the idea is to use several convolutional layers in parallel with different kernel sizes in each convolutional layer. So this is sort of the idea. This would be the the tensor, the feature map coming out from the previous layer. And this is showing that you're going to simultaneously do, or in parallel, do a 1x1 convolution, a 3x3 convolution, a 5x5, and another 3x3 with max pooling. And then you're going to stack the results of each of these, concatenate them into the next tensor. And what this allows you to do is, if you have a bigger kernel, use fewer channels, right? And that was what we saw in this equation. The number of coefficients, you can see as the kernel gets bigger, this grows a lot. So to compensate that, you can decrease this. So that's the idea. Decrease the number of channels for the bigger kernels. Another advantage of this is that when you use kernels of different sizes, you can help to make the features they look for scale invariant, meaning sometimes there might be a small picture of the object, other times a big picture of the object, and by having kernels of different sizes, you can better handle the different sizes of objects when you're trying to do classification. So those are some of the ideas that they used in GoogleNet or Inception v1. If you like to read more, there's a good overview in this article. So that's and this is 22 layers compared to 16 for VGG or 19 or so. So you can see the number of layers is still growing. But as they kept pursuing that path of trying to get the networks deeper, they ran into another problem. They found that these networks are getting more and more difficult to train as they got deeper. And previously we talked about one reason that depth can be difficult, which is vanishing gradients. And we said that, especially if you try to use sigmoids or tanh-H's, you run into this vanishing gradient problem. So by using ReLU and batch norm, you can tame the vanishing gradient problem. But it's still, it's still there a little bit, but that wasn't actually the problem that people were seeing so much as another problem called the degradation problem. So one thing they saw is as the networks got deep, even the training error was increasing. So it's not a matter of overfitting. You might say, like, if my network is too deep, maybe I'm overfitting. In that case, you would see that the training error would get better and better, but the testing error would get worse and worse. They're actually seeing the training error get worse and worse. So there's something sort of fundamentally about the way these networks are constructed that is causing problems. And so some intuition comes from the following idea that when we stack, concatenate layers onto each other, if layers can act like identity functions, there should be no penalty for adding those layers, right? Because, I have a layer that's learnable. It can do different things. So if I can possibly learn the identity functions, I shouldn't have problems. So the fact that we are having problems, you could say, is due to the fact that the layers we have, these convolutional layers with ReLU, they are not good at mimicking identity functions. So if you make a network maybe longer than you need to, you can't set those layers to act like identity, and then they start causing problems. So that's sort of some of the intuition. If network layers can act like identity, they should be able to perform at least as well as shallower networks. And if you think about it, convolutional layers, especially with ReLU, because ReLU cuts off the negative parts, it's just hard to make those function like an identity. So the idea was to help them act like an identity by adding what they call a skip connection. Sorry, I don't know why this is blinking on and off. But the skip connection, as you can see, if you take the details of this are not so important. This is, as you can see, it's like a linear layer, a ReLU, and another linear layer. But the point is, by adding this skip connection, you can make this whole thing act like an identity just by turning the weights either here or here, making them small, making them go to 0. And then that means that if you have a very deep network, and you don't really need it to be that deep, you can just turn some layers into identities, and they don't hurt you. Their presence is not going to hurt you. It's not going to cause problems. So that's one way of understanding the construction of these residual networks. And so this was introduced in late 2015 by Microsoft, and it was called a ResNet, and it was a huge breakthrough. And this actually allowed them to construct deep networks successfully with hundreds of layers. In fact, I think even in some cases thousands of layers. So in 2015, they won that competition with a 3.6% error rate, and if you remember, previous winner was 6.7. So again, another leap forward. Now this was slightly lower complexity than VGG16, so as you can see, it definitely had way more parameters than Inception V1, but it does do quite a bit better in terms of performance. All right, so any questions on residual networks so far? Is this making sense what the skip connection is doing? All right, so there's another way to think of these networks, which is maybe even a better way or the right way. So when you think about, this is just a short 3-layer ResNet where you have something in here and you have a skip connection, then again something in here, something like a convolutional layer with a ReLU. Another way to picture what's going on here is to unravel this and think that there's basically 8 different ways that data can flow through this 3-layer network because there's a binary choice at every layer. So, one way is to go through all the skip connections. So that's one of 8 possible ways to go through. Another way at the other extreme is to go through all those functions. So that's another way. But then there's 6 other ways in between where maybe you're going through one and not the other, and so on. And so here you can see this is unraveled into 8 different possibilities. And when you think about it this way, it's actually you might ask, like, okay, so I have this network that has, you could say, subnetworks in parallel with many different path lengths. Like, so this is a path length of 3, this is a path length of 2, these have path lengths of 1, and then this guy has a path length of 0. So you could say, like, how many subnetworks will we have with a given path length? And it ends up being, so the number of, let's say, subnets with path length p is given by the binomial coefficient. It's going to be L choose p. So this gives you a sense for, how many you're going to have of these different lengths. And when you look at how these coefficients look for different p, you find that most of the paths have a length of around L over 2. And if you plotted a histogram of them, it would look kind of like this, almost Gaussian looking. So this is, so L would be the most, 0 is the least, and this is a distribution of P, path length. So this tells you that, for example, if you have a 110-layer network, that really most of the paths in that network are around length 55. But there's another issue, is that when you look at those different length paths, the longer ones contribute less of a gradient than the shorter ones because they have more of these ReLUs to go through, and the ReLU is cutting off half the signal and so on. And so as a result, when you combine these gradient issues with this binomial stuff, you find that, for an example, in a 110-layer network, the only paths that are really contributing to this unraveled view are paths with length about 10 to 34. Okay, so this gives us a completely different way to think about what's actually going on in a deep ResNet like this. It's really like you have a bunch of networks, shorter networks in parallel with lengths between 10 to 34, and they are working in parallel to get the classification done. So really what's going on here is we have an ensemble of shallow networks. So ensembles are things we'll talk about in the next unit. It's basically when you have like a whole bunch of weaker classifiers all working together, or weaker regressors all working together to do a task better than any of them individually could do. So in some sense, you could say a ResNet is working that same way. And there's a nice paper about that, which is, if you follow the link here that I highlighted. This also led to some other ideas about how you train them. Basically, in a ResNet, if you remove one of these layers, as you can see, it's maybe not that big of a deal because the information can flow around it. And actually, this can be helpful. It's similar to dropout, but it's basically dropout at a layer level, where during training you randomly drop out layers. And this can help to speed up the training of the ResNet and reduce overfitting, similar to how we were dropping out nodes with, with other convolutional or dense networks. So, this is just another view of ResNets and how they work. All right. Any questions with this? Okay. All right. So, so as time went on, there were many other networks proposed. Like there was Inception v2, Inception v3, which is nowadays kind of an important network. People still use the features of this quite a bit for other tasks. Inception v4, Inception ResNet, and so on. And there was, various little tricks they used. There was more efficient inception modules. In some cases, there's these auxiliary outputs where they take an output off the side of a network, and so on. And like Inception v3 took second place in the 2015 competition. So people kept inventing, new things that helped. DenseNet was an idea in 2016 that was sort of like a ResNet on steroids. And so in DenseNet, what you do is every layer you connect to all previous layers, whereas in a ResNet, this would only be connected here, and then maybe this one would be connected here, and so on. So this is a much more dense way of connecting things, and then you have these dense blocks that are densely connected, and then you have a cascade of them. So this outperforms the ResNet and does pretty well. After that point, at least for image recognition, people stopped trying to make the networks perform better. They, at least in terms of just accuracy, they focused more on making them more lightweight, more applicable for mobile implementations, meaning like less memory needed, less computation. So for example, this SqueezeNet in 2016 achieved AlexNet-like performance, but with 50 times fewer parameters. And MobileNet in 2017, again, very efficient memory and computation, still highly accurate, and so on. So that's kind of a history. You can see how things evolved over time, and maybe you've heard of some of these. Maybe you've heard of a ResNet and stuff. So now you know what it is. Any questions on any of this about the progression or anything else? Okay, so now we'll kind of change gears and we'll talk a little bit about how to use these pre-trained networks in PyTorch. So again, the first thing we do is we have to import the Torch Vision models package, and then you can see we can just download the VGG model, and we can tell it if we want the weights or not. Obviously, when you bring down the weights, that's a huge amount of data that comes with it. And when you print the model, you can basically see all the different layers. So in this case, VGG has basically, you could say, 3 different stages. There's the feature generating layer, which is basically 13 convolutional layers with ReLU and MaxPool. And then at the end, there's the classifier layer, which is 3 dense layers with ReLU and Dropout. And then in between, there's this interesting layer called an average pool or adaptive average pool layer. And what that layer does is it helps you handle different sized images. So without it, I think without it, basically you would need to use exactly one image size, because if you think about the way convolution works, if you start with some image size here, as you convolve it with different kernel sizes and you do different subsampling or pooling, you would eventually get, at this point, a tensor of a very particular size, right? And the size of the tensor would depend on, at least the number of pixels high and wide would depend on the original image size. At the point that you transition from this tensor to the first dense layer, you need to unfold or unravel that tensor into one long vector. And when you go through these dense layers, you have to have exactly, in this case, 25,088 features. You can't have more or less, otherwise it doesn't work. So that would make, if you didn't have this adaptive average pool, you would not be able to handle different image sizes. But what this allows you to do is it allows you to handle different image sizes. So the way that it works is you get a tensor at the input of this. Then in this case, it's going to have 512 channels, and it's going to have some height and width in terms of the pixel dimensions. And what that layer does is no matter what that height and width is, it will resize it to 7 by 7. And at 7 by 7, you find out that 512 times 7 times 7 is 25,088. That's the number you need to interface with those dense layers. Okay, so this adaptive average pool gives you that flexibility. You can use images that are smaller or larger than whatever the default is. I'm not sure if maybe without this, maybe it would expect the image net size. Okay, so that explains that adaptive average pool. All right. Otherwise, you can see like exactly what they did at every layer. You can see how many channels they use. You can see what the kernel size was. You can see if there's downsampling. This padding basically tells you the kind of convolution, like is this going to be valid mode or whatever. And yeah, you can see the dropout with the probability and so on. All right, so let's do a little experiment where we use this network. We're not going to modify it. We're just going to use all the trained weights. And so we need to download some data. So a great way to get image data is Flickr. It's like a photo sharing site. So in order to do this, you need to get some API keys from Flickr. You need to register with Flickr. It doesn't take very long. Once you have those keys, you can download images from Flickr by just giving a keyword like elephants. And you can just keep pulling down elephant images, and you'll get elephant images, or at least images that Flickr thinks are based on elephants, in various sizes. And they'll come in, and you can see the demos in this, the demonstration in this demo C. So to work with this, we're going to make separate test and train directories. And within each of those, we're going to make different subdirectories. In this case, we only have one class, elephants, but I think in the lab you have cars and bicycles, so you would have like a cars directory and a bicycles directory. Anyway, here are the images we've downloaded. You can see these are not very high resolution. These are all elephants. Honestly, pretty hard to tell that they're elephants, but as you'll see, our neural network will still do a pretty good job of classifying them as elephants. Okay, so the steps to get this working are we use this image folder function to create a dataset object. This supports various normalization, resizing, and augmentation transforms. We don't need our images to be 224 by 224 because adaptive average pool. And in fact, so here what you can see we're doing is we're going to crop our images down to 200 by 200. This number can be adjusted depending on your hardware. If you use larger images, it takes more compute power to get the images through the network. So if it's running too slow for you, you can just make that smaller and it will run faster. Once we have the dataset object, we can use the data loader to draw mini batches out. So this transform object is something that basically you can see it can do a sequence of steps. The first step we're going to do is we're going to convert to a tensor, and then we're going to apply our crop. But you could also do other things like flip the image, zoom in, change the colors. There's all sorts of different things you could do in a list of transforms. Now we're going to tell PyTorch where to find our data and which transform to use, and that's going to construct a data set. And then we're going to give that data set to our data loader, and we're going to tell it what batch size to use, and then it's going to be able to draw batches from our data set. And this is the batching command. You can see next iter loader produces the image X, and then its label Y. Okay, so now we can classify. Remember, our network is trained, so we don't need to retrain it at all. So we just put the model in evaluation mode, and what that does is it prevents the model from calculating, from doing the back propagation, from computing all these gradients. So in this eval mode, it just does the forward pass. And actually, there's a couple different things eval does. So like eval will turn off dropout, because dropout is something you do at training but not test. And then actually it's this command, torch nograd, that prevents the computation of gradients. So with Torch Nograd, we put our image through our model to get an output. This output in this case is a bunch of scores. And so we want to turn those into probabilities so we can put it through softmax. And now this new vector will be a probability mass function. So it's a sequence of probabilities that sum up to 1. And now we can use this output.topk command to extract the top 3 probabilities in that vector. And we're going to say this is what their values are, this is what their indices are. And then that is going to, once we know those indices, remember this is all trained for ImageNet. So ImageNet has 1,000 classes. Each one has a particular index. So now that I know the indices of, let's say, the most probable guess, I can look up in a table, and I can look up for that index what is the class. So you can see here Indian elephant, African elephant, tusker. It's doing really well on these 10 test samples, except here we have leatherback turtle. That's the only mistake it looks like it's making. We're feeding it in elephant images, but it doesn't know they're elephants. It just knows about ImageNet, and it's successfully figuring out that these are in fact elephant images. And that's the most probable class. And here you can also see the probabilities are reasonably confident. The second guesses are also in many cases pretty good, but here we have water buffalo. Interestingly here, the one with the leatherback turtle, the second guess is an elephant. Third guess, Komodo dragon, and so on. And then we're using a pandas data frame to print this out nicely. So you can see we're basically just downloading a pre-trained network, getting images from somewhere else, putting them through the network, and verifying that, yes, this is actually working really well as a image classification network. Okay, any questions on any of this? Okay, so another thing we can do is we can take a peek at the internal variables of the network, these feature maps. So to do this, we build a new little, a new class, which we're going to name feature extractor. And this class is going to take in, when we initialize it, we're going to tell it which are the feature layers in our network and which are the classification layers. And remember, we know that because we know the structure of this network. These are all the feature layers. These are all the classifier layers. And so what it does is it basically stores those internally and stores the model. We're also going to pass in the model, stores that internally. When we do the main function here, we put data through this forward pass, and you can see that it's going to initialize these empty arrays of feature outputs and classifier outputs. And now what it's going to do is it's going to go one by one through the different stages in the network, through the different layers. And so first it's going to go through the feature layers. It's going to put the representation through the next layer. And then if it's a feature layer, it is going to take that representation and it's going to basically add it to this list of feature layers here. So it's basically going to build up a list of what it's seen at the different feature layers. So it does this through all the feature layers, then it goes through this adaptive average pool. And you can see there's a flattening step here to prepare for going through the classifier modules. And then it's going to put the data through each of those classification layers, and it's going to add the output to this array. And finally, it's going to return the feature and classifier outputs that we want to look at. And so this is an example of what it sees. So here we have this image, the original image. We're just showing you the red, green, and blue channels individually. When we go through the first layer, it's going to grow the number of channels. I can't remember exactly how many there are, but as you can see, there's a bunch of them. There's definitely more than 3. But it also is going to shrink the image size. It's going to have it. So, and now you can actually see like that initial convolution and ReLU, this, it did particular things. Maybe it was doing something like an edge detection, or maybe some sort of looking for some sort of texture. But you can see that here in these different layers, the outputs are all a bit different, and they're just, it's computing features that will eventually be used for classification. If you go all the way to layer 10, now the feature maps are quite small in terms of number of pixels. It looks like there may be, I don't know, maybe like 14 by 14 or so. And there's going to be a whole bunch of them, but this is just what the first 4 look like. And now you can see that they really look nothing at all like the original elephant. At this point, they have a completely different meaning. It's generating these features that are eventually going to be useful for actually doing the classification. So as we go through the network, we start in the image domain, and we gradually go and get less and less about images and more about those 1,000 classes. All right, so that kind of concludes looking through this demo. Are there any questions about anything we've seen here? Okay, no. All right, and then I just wanted to briefly, just one more slide about other applications of deep learning, and just to try to give you some scope. So we have focused pretty much exclusively on image classification in this set of notes, and this is just one of thousands and thousands of different tasks you can do with deep learning. Even it's just for imaging problems, it's just one of many, many tasks. And so I'll just briefly tell you about some other tasks. So like one that you may have heard of is called object detection. So this is what we've been talking about, image classification, where basically you're given an image and you want to say just what is that image overall. So this image, you're saying, okay, I want to recognize that that's a cat. Object detection is related but different in that you're given an image and you are asked to find all the different recognizable objects in that image, as well as where they're located. So here, you hope that your network says there's a dog here, there's another dog here, and there's a cat here. Maybe it would also say there's a tree here, and a pillow here, and a couch here, or whatever. But you can get the flavor of object detection versus image classification. Okay, now there's another related but different thing called segmentation. So segmentation is where for every pixel you want to classify that pixel as one of a few classes. In this case, you're going to basically say there's 4 classes. In other words, every pixel in the image is either going to be a grass, cat, tree, or sky pixel, and I want to classify every pixel. In other words, I want to label every pixel with that color. And so you can see that it did a pretty good job here of getting the sky, of getting the trees, the cat, and the grass. So that's called segmentation. Now there are some kind of mixtures. This thing, instance segmentation, is sort of a hybrid where you want to identify within this picture. First of all, you want to detect that there's a dog here, but then you also say exactly which pixels are attributed to that dog versus the background versus this other dog versus this cat. And then there's classification and localization, which I probably should have talked about earlier. That's similar to this, except in addition to saying there's a cat there, you want to say, where is the cat located? Okay, so these are just different flavors of classification and object detection. Those are just a few things you could do with images. Before we move on, are there any questions about any of these? No? Okay, so we basically talked about object detection, image segmentation. Now, very differently would be image compression. So we're all familiar with JPEG as an algorithm to compress images. Well, you might ask, could I learn to compress images better than JPEG? The answer is yes. So you could train a deep network to do that compression. You might have a task called image denoising, where someone gives you a very noisy version of an image. Your job is to remove the noise and try to figure out what is the clean image underneath. Deblocking is where they give you, I think you've all seen that sometimes standards like JPEG can give you blocky artifacts, especially if maybe you're watching digital TV and then there's some problem with the transmission and all of a sudden like you'll get some pixels that are very blocky. So you might say, can I build a deep network to clean that up? So that would be deblocking. Deblurring would be an example where somehow you have a blurry image and you want to make it sharp. So this was kind of famous a number of years back with the Hubble telescope that went out into space, and when they deployed it, they realized that there were some problems with the mirrors, and so all the images they were getting back were blurry, and they weren't out there, they couldn't figure out what the exact shape of the mirrors was, so they had to figure out how to deblur them without really knowing exactly how the blurring happened. So this is an example of deblurring. This is another thing you can train deep networks to do. There's many other forms of image recovery. So super resolution is when you have a small image and you want to make it large. If you did that using traditional techniques, you just get a large kind of blurry image, but you want to make it large and sharp. So that's what super resolution is. Phase retrieval is when you, there's some applications where you measure the signal in the Fourier domain rather than the pixel domain. And in those applications, there are cases where the sensor can't give you the phase. It can just give you the magnitude of the Fourier domain, not the phase. And so phase retrieval is the process of trying to figure out what the phase is so you can merge that with the magnitude information and actually figure out what the image was. So this is used in X-ray crystallography. It's used in some kind of interesting applications where if I want to look around a corner and what I can see is that there's a rough wall surface, you can actually learn how to use that wall as a mirror, use its rough scattering as a mirror using phase retrieval techniques. So there's a number of cool applications of this. Other image recovery would be magnetic resonance imaging. This is an application where you measure things in the Fourier domain, but you don't get to measure enough samples to satisfy Nyquist's criteria. So you have to try to figure out the missing information or recover the image. Computed tomography is another medical imaging technique, and it's also used for X-ray scanners and stuff in airports. It's another case where you don't measure exactly in the Fourier domain, but in another domain where you don't get all the measurements you want, and so you have to recover it there. In painting is an example where maybe I give you this picture, but I leave out these pixels. And so you can see, you know that there's a tail there, you know there's a foot there. Can you fill in the missing pixels? Sometimes that's useful, for example, if you have an image with text written on top of it. You want to remove the text and figure out what were the image pixels underneath it. So you can do that with in-painting or image completion. And then another kind of different application is image generation, where you say, generate me an image of a cat. I want you to be able to generate many different cat images or whatever. That's image generation. And I think recently this has been very popular in text to image, like DALL-E and other things where you type in a few words and then it will generate an image of the text. So pretty fun stuff. And this is just imaging. There's many, many applications outside imaging. You can see the scope of what this stuff has been used for. It's just, it's endless. So when you design networks for all this stuff, sometimes they look similar to things that we've seen. For object retrieval and a lot of those, classification, segmentation, well, some of them look similar, but other ones look kind of different. Like, actually for segmentation, you need a network that takes in something of this many pixels and also produces something of this many pixels with a discrete label on every pixel. So all the networks we've talked about start with something image size and go to something with the number of classes. But in this case, you want to start with something image size and end with something image size. So for that, the UNet is a very famous network. Another different kind of network structure is recurrent neural networks, where you have a network that takes in data and puts out data, but then it also uses the output and feeds it back to the input and kind of goes around several times. So there's some issues with recurrent neural networks that make them challenging, but this long, short-term memory networks have been proposed as sort of a way of helping with some of those issues. There's these autoencoder networks that basically, they take in something like an image, they distill it to a few components to figure out really what is the essence of that image, and then they can zoom back up to the original image size. Generative adversarial networks are things that are used a lot for image generation. You can also use these autoencoders for image generation. Normalizing flows are kind of a newer family of networks where you build a network that is invertible. So if you go one direction, you're guaranteed to be able to go back the other, and there's a number of nice things about that. Transformers are a new kind of class of networks that are not based on convolution. They're based on a more general operation that can be really important in some applications, especially natural language processing. So this is just a few buzzwords, but there's, as you can see, deep learning is pretty big field. We would like to be able to offer another class to continue this one. Right now, we haven't been able to do so yet, but maybe in the coming years we can basically talk about a lot of this stuff in a follow-on class to this one. So that is all I have for this unit. And what we'll do on Monday is we'll do a review. And remember, next Wednesday you have your second midterm. It does not cover Unit 9. It covers Unit 5, which is where we first started talking about classification and logistic regression. 6, optimization. 7, support vector machine. And 8, two-layer neural networks. But not this one. So on Monday I'll do a review. Are there any questions about any of this stuff, or? Yes?
Is autoencoder something like singular value decomposition and taking some top vectors or top eigenvalue vectors and rejecting some other vectors?
I wouldn't say it exactly that way, but I would say an autoencoder is kind of like, it has an encoder network and a decoder network. And usually the way you think about it is, when you see an image, there's a lot of redundancy in all the pixels there. And you might ask the question like, can I find some representation of that image that requires many fewer pixels? And that's sort of what the encoder does. Now, in order for you to make sure that you haven't lost important information, you want to also make sure that if you have a decoder that takes that information and goes back to the image domain, you actually have the same image you started with. So you really haven't lost much. So that's sort of what the autoencoder does. Now, once you have that representation, you can, like what you actually typically do is you force those middle, what they call latent vectors, to look Gaussian. So you train them so that they look Gaussian. And once you have that, you can maybe forget about the encoder network. Now you have the decoder network, and you can feed in random Gaussians, and maybe they'll come out looking like images from your training set, but different ones than you've ever seen. So you could use this as a generative network. You could also use it as a denoiser. You could say, like, I'm going to train this thing on images in my data set, and it's going to be able to produce images, but if I put in noise, the encoder network will filter out the noise because it's not used to seeing that, and then I can build a denoiser out of it. So there's all sorts of things you can do with autoencoders, different applications, but they all have that sort of squeezing. It's like an hourglass, squeezing and expanding. All right. Good question. Any other questions? All right, if you have questions, you can see me after class, but otherwise, have a great weekend. See you guys on Monday.